If I wouldn't have asked you to help me, Matthew, I would have totally forgot
I honestly already forgot it.
that. Okay, so today we're going to try to finish off chapter 21. And even the stuff that I don't necessarily get to will still be, you'll still be able to do it because it's pretty straightforward. What I try to do in each of these chapters is take the hardest stuff that I think is the most difficult for you to grasp and get, and I try to work those for you and in a way that it's really explanatory and helpful, hopefully. Okay, that's my goal. I don't know that I always succeed, but that's my goal. So I'm going to start off with talking about chapter 21, not about the concepts, because I think the concepts are interesting and not necessarily always easy, but I think they're pretty tractable here. Just after giving you that intro to the MIT video, for instance, that's a pretty good step towards that way. What we do is we introduce Coulomb's law as F is equal to K, Q1, Q2 over the distance between them squared, and mention the fact that just like the equation for gravity, the force in this case is not just attractive, it can be attractive or repulsive, but just like in gravity, it's going to be along a line connecting the center of charge of each of the charges. So in Newton's law, F equals G M1 M2 over distance between them squared, and it was said that the force acts along a line connecting the center of masses of the two masses. If we start with just particles, then there's no ambiguity about what the center of charge is. It's just where the particle is. And it turns out if it's spherical and uniformly charged, then the middle of the sphere acts just like it's a part. The whole sphere acts just like it's a particle at its center. So you can just use that over and over again. But then we're going to go into more detail where we're attacking problems that are continuous distributions of matter instead of point particles, and we pretend like they're little point particles that we divide them up into, and then we sum them up via the calculus. So it's going to get a little more complicated. So let me go ahead and turn on my iPad, and I've had some issues with it turning off and not being able to connect. Hopefully I won't have any problems this time. So I'm going to share the iPad screen with you. It's going to tell me to do screen mirroring, which all of a sudden it's stopping doing for some ungodly reason again. Come on now. Everything's just sort of going real slow right now. I don't know what's happening. Make sure my phone's not on this network. My phone is not on this network. Maybe Zoom is being a jerk. Yep. Okay. That's what it is. Somebody was coming in at the same time. So hopefully I can now do it. Looks like I can. Yes. Whew, scary. Scary times. Okay. So we've now got screen mirroring on here. And what I want to tell you is, first off, I'm going to tell you what Coulomb's law is. And Coulomb's law is F is equal to K Q1 Q2 over R squared. General idea that you want to keep in mind, this is more for my algebra-based and my conceptual physics, but we don't get to talk about the concepts enough in calculus-based physics. So I want to point out something that's supposed to be obvious, but if you haven't thought about it, it's not. If you compare two variables on opposite sides of an equation, so for instance, we got F on the left-hand side here, and we've got Q1 on the right-hand side. If they're on the same side of their fraction bar, then they're what we call thumbs up, thumbs up. Okay. Now the F might be somewhat ambiguous as to whether it's a numerator or denominator, but remember, you can always write a number as itself over 1. So F over 1 really tells you the F is in the numerator, and Q1's in the numerator. So they're thumbs up, thumbs up. What that means, if I double Q1, I'm going to double the force acting between Q1 and Q2. Q2 is also on the top. So if I double the charge on Q3, that would double the force as well. But we can also take it a step further and say, if I doubled the charge on Q1 and let's say quadrupled the charge on Q2, then I would increase the force by a factor of 2 times 4, which is 8. The other side of that coin is we have F and R. They're also on opposite sides of the equals sign, but the R is in the denominator and the F is in the numerator. So they're thumbs up, thumbs down. And not only that, it's not R, it's R squared. So if I, for instance, increase R by a factor of 2, maybe I go from 1 meter away to 2 meters separation. If I do that, then the force will go down by a factor of not 2, but 2 squared, which is 4. If I decrease, let's say from 4 meters, I turn it to 1 meter as a distance between them, then I have decreased the distance by a factor of 4, which means the force should increase not by a factor of 4, but by a factor of 16. Does that make sense to everyone? That's something you can use every time you see an equation. You can just compare variables on opposite sides of the equal sign and realize they're thumbs up, thumbs up. It means if one increases, the other increases when you have thumbs up, thumbs up. Are they directly related in some sense? If they're thumbs up, thumbs down, that means they're indirectly related. Like the higher your average speed in your car, the lower the fuel consumption. Or excuse me, the lower the fuel efficiency, miles per gallon decreases the faster you go. All right. So when we use this for version of Coulomb's law, the K doesn't really have a name, but the number is 8.988 times 10 to the 9th newtons meters squared, and then the unit of charge is the Coulomb. So it's a Coulomb squared. Now, Coulomb's a big unit. It's not unreasonable to imagine a lightning strike carrying or delivering maybe 500 coulombs. So that gives you an idea. Yeah, that's a pretty big amount. Also, I should say historically, I can't remember who the other person was, but Coulomb was one of the people that did an experiment that determined this relationship between the force and the charges and the distance. Ben Franklin was another one that might have even beat Coulomb to the punch, but there was a third person too who escapes me for some reason today. I was thinking it might have been Poisson, but I don't think that's the right time frame. But anyways, there's another version that actually uses a constant that's more meaningful to us. So it looks kind of crazy that we take the time to write it this way since it's so much more complicated to write, but it's Q1, Q2 over 4 pi epsilon naught R squared, where epsilon naught is 8.85 times 10 to the negative 12th Coulomb squared per Newton meter squared. That's called the permittivity of free space. That 0 subscript means it's for a vacuum, but it's really very close to that even for air. If we left off the 0, that would be, say, inside of a what we call a dielectric, which is an insulator, or inside of a conductor or something like that. So it's a permittivity. It's an actual physical parameter that we can measure. And in fact, it's related to the speed of light. So that's why one of the reasons that we tend to use it this way, 4 pi epsilon naught instead of K. It doesn't matter which one you use, just long as you use either the K or the whole 4 pi epsilon naught in the bottom. Okay. The other thing to notice is, remember, the force is either attractive or repulsive. Like charges repel and unlike charges attract. So you can remember the old adage that opposites attract. That's what a lot of people say about relationships. Well, it's really true with charges. A positive and a negative are attracted to each other, whereas a positive and a positive try to repel each other, and a negative repel each other. Everybody got that? All right. Now, another scenario is, or another thing is, charges seem to come in discrete amounts. A guy by the name of Millikan did an experiment called the Millikan oil drop experiment, and he found that sort of the smallest unit of charge was given the letter E, which is like the electron. It turns out to be the charge of the electron, only a positive value, where electron turns out to be negative. It's 1.602 times 10 to the negative 19th coulombs. That's the electron charge when it's negative. It's the proton charge when it's positive. Okay. Some other constants that come in handy for this class in general is the mass of the electron. which is 9.109 times 10 to the negative 31 kilograms. Also the mass of the proton, which is 1.673 times 10 to the negative 27th kilograms. And just for good measure, the mass of the neutron is equal to 1.675 times 10 to the negative 27 kilograms. Those are just things we occasionally use. I'm not requiring you to memorize the mass of electron, proton, or neutron, but I do expect you to know epsilon 0, K, and E. So you should know this one, and this one. The other ones, of course, I will give you if you need them. So just to give you some feeling for types of calculations we'll do, one thing we want to do is we notice how much this force looks just like the equation for gravity. In fact, the equation for gravity is F is equal to G M1 M2 over R squared, where G is equal to 6.67 times 10 to the negative 11th newtons meters squared per kilogram squared. Okay, you should be able to tell already, given that G is 10 to the negative 11th, it's like 0 followed by a decimal point followed by 10 zeros and then a 6, whereas the K in Coulomb's law is like 9 billion. Okay, so that already makes you think that maybe the Coulomb force is 1 with 20 zeros after it times stronger than the gravitational force. Everybody see where I came up with that 10 1 followed by 20 zeros?
No.
Okay, that K, if we just ignore the 9 part and say it's 10 to the 9th, and I divide that by ignoring the 6.67 part and divide it by 10 to the 11th, negative 11th, 10 to the 9th divided by 10 to the negative 11th is the same thing as 10 to the 9th times 10 to the 11th. And of course, that's 10 to the 20th, which is 20 zeros. Now you see what I'm talking about?
Yeah.
Okay, so let's actually consider for a second, and here's another variable that comes in handy, and that is the Bohr radius. This is one you don't need to know. But when Bohr worked out his quantum mechanical hydrogen atom, he actually got exactly the right answers for hydrogen, but only hydrogen. And he found that the Bohr radius was 0.5292 times 10 to the negative 10th meters. So we can actually compare the force due to Coulomb to the force due to gravity by dividing the force due to Coulomb by the force due to gravity. And of course, that would be, notice it's going to be K Q1 Q2 over R squared divided by G M1 M2 over R squared. So the R squared is really going to cancel out. Let's do an order of magnitude approximation. So for instance, we'll just say this is 9 times 10 to the 9 times 2 times 10 to the negative 19 times 2 times 10 to the negative 19. See, it's 1.67, but that round, or excuse me, 1.602, but that rounds to roughly 2. And that would be over A0 squared. And then this one is about 7 times 10 to the negative 11 times the mass of the electron is about 9 times 10 to the negative 31. And the mass of the proton is about 2 times 10 to the negative 27. And then, of course, that's over A0 squared as well. So those A0 squared are going to cancel out. And we can actually get, notice the 9 will cancel out with the 9 over here. This 9 multiplied 10 to the 9th times 10 to the negative 19 gives me 10 to the negative 10. And then 10 to the negative 19 times 10 to the negative 10 would be 10 to the negative 29th. So I get about 10 to the negative 29th. Of course, that's 4 times that, because 2 times 2 is that. And then on the bottom, I get 10 to the negative 11, 10 to the negative 31, 10 to the negative 27. That's 58, 68, 69. So this is 14 times 10 to the negative 69, which I think you can see is about equal to 10 to the 38th. Or excuse me, 10 to the 39th. That writing looks horrible. Okay, so what that means is basically the Coulomb force is about 1 followed by 39 zeros times stronger than the gravitational force. So throughout the semester, we're not going to be thinking much about gravity. Any questions on that? So this is just a typical type of calculation to get some feel for exactly what is or how big do these forces get compared to one another. So yeah, you should think that the electric force, which turns out to be about the same magnitude as the magnetic force as well, you should think that they are both much stronger than the gravity force, and in fact it is. Not only that, we can jump from one coordinate system to a different one, moving at a speed relative to the first one. And when we do so in just a certain way, literally the electric field in one frame will disappear and become a magnetic field in the other frame with the exact same size. So the electric and magnetic fields are really just two sides of the same coin. That's why we call it the electromagnetic force, because it's actually two sides of the same coin. We'll later learn a equation like Coulomb's law, only it's got awful ugly. There's a cross product in it and a unit vector in it and all sorts of crazy stuff. So anyways, we'll get to that, and it's not as bad as it seems, but it is kind of scary when you first see an integral with a mu 0 I over 4 pi times dl cross r hat over r squared, blah, blah, blah. And you're like, oh God, this is the most awful thing ever. What I'm going to do now is actually take one of the more difficult problems, like what your book has, and solve that in a fairly robust way so that you can get some understanding of how to do Coulomb's law problems, at least for discrete particles. So what I'm going to do is I am going to create an XY coordinate system. And then I'm going to put a mass here and a mass here and a mass here. And in fact, they're actually charges. Okay. I'm sorry about how they fell off the line and everything, but that's just typical, I guess. Now what I'm going to do is I'm going to say that this one happens to be about 40.0 centimeters over. This one happens to be about 30.0 centimeters over. Actually, I should probably write that somewhere else. So. Okay, so this was just 30 centimeters. All right, this charge right here is going to be Q1, and it's going to equal negative 60 microcoulombs. This charge right here is going to be Q2, and it's going to equal positive 50 microcoulombs. And this charge over here is going to be Q3, and it's going to equal to, actually, I'm going to change that Q1. Sorry about this, guys. Let me change this Q1. I'm going to change that to negative, yeah, let's do negative 80 microcoulombs. Okay, and then Q3, that's the one I want to be 60 microcoulombs. Okay, so what I want to know is what is F3. Notice that's a vector quantity. Okay, so I want to know what is the force magnitude and direction on Q3 as a result of Q1 and Q2. So I'm going to start writing my solution by choosing another color. So what I say is F3 is actually the force on 3 due to 1 plus the force on 3 due to 2. Does that make sense to everyone? So I'm going to write down F31 right here. And what I realize is F31 is the force between Q1 and Q3. Now Q1 is negative and Q3 is positive. So are they attractive or repulsive?
Attractive.
Yep. That is what we do to decide the direction of it. And in fact, we know this side right here, since this is 40 centimeters, that's 30 centimeters, then that means we're working with the 3, 4, 5 triangle. So we know that the hypotenuse is 50 centimeters. And since it's attractive, we know this force acts straight along here like that. That's F31. Or excuse me, yeah, F31. Does that make sense? So now I can calculate the magnitude by saying 8.988 times 10 to the 9th. I'm going to leave off the units. It's actually good practice to keep them, but I'm leaving it off. And I never put the signs in. So I'm going to do 80 times 10 to the negative 6, and then 60 times 10 to the negative 6. And all that will be divided by 0.500 squared. When I do that calculation, I'm going to put that in. I get 172.6. Actually,
Question.
Yes.
So the signs don't matter here?
Yeah, that's what I'm trying to advise you to do, is never put the signs in. You're going to use your understanding of the physics concepts to decide direction. And like, for instance, the problem that we skipped was a problem that your book did where it put 3 charges in a line in a row along the x-axis. What you'll do with that is when you consider the force on the from the far left one on the far right one, you first decide, is it attractive or repulsive? If it's attractive, that far right one will be pulled to the left. If it's repulsive, that far right one will be pushed to the right. And in that case, you take the x-axis as if it points to the right in the positive direction. So if it was a repulsive force, it would be called positive. And if it's an attractive force, it'd be called a negative force, because in one dimension, the direction of a force or a vector is just its sign. So yeah, always use just the plain positives, and then use the geometry and the fact that it's attractive or repulsive to decide what direction it goes in.
Gotcha. Thanks.
Okay, no problem. So that's F31. Now, in reality, I also need F32. So I'm going to write F32 over here. And I need to find out, are they attractive, or is that force attractive or repulsive? So Q3 is positive 60 and Q2 is positive 50. So are they attractive or repulsive?
Repulsive.
Repulsive. So now what you want to do is realize that, okay, the force has to lie along the line that connects the centers, just like it did on the 3-1 case. So in this case, it has to lie along this line. And in fact, it'll be right there, F, since it's repulsive, it'll be F3. Whoa, that was bad. Okay, it'll be F32. Okay, so in fact, it has only a y component and no x component. I'm going to break this vector up into this F31 into an x component. And I'm going to break it up into a y component as well, which I'm going to make red because it's negative. Okay. And notice that angle right there is the same as this angle right here. Okay. So we can go ahead and first work out the magnitude of this force, and then we'll take the F31 and find its magnitude and direction as well. So first off, I'm going to go ahead and compute the magnitude of F32. So that's 8.988 times 10 to the 9th. And actually, sometimes it's a lot more efficient to write like Excel does. So I'm going to say the charge on Q3 is 60 E negative 6, and the charge on 2 is 50 E negative 6. And then all of this, of course, is divided by 0.30 squared. And I should try to separate this so someone doesn't confuse those. Sorry, it got so small there. Go back to this. Now, this force turns out to be, when I punch it in my calculator, this is F32, I get 299.6 newtons. Now, notice what I'm doing here is we only had 2 sig figs on the charges. So I underline the 9 and the 6 here, and the 2, the 5, and the 7 there to show that they're really not digits I'm supposed to be carrying, but I always carry at least 1 extra digit in intermediate calculations. Now, because F32 points purely upward, I can say F32 X component is 0. And I can say F32 Y component is in fact positive 299.6 newtons. Okay. I can say F31 X is going to be positive 172.57 times the cosine of phi. Well, I will tell you that phi is in fact 36.86 degrees. And that's because the 3-4-5 triangle, if you take the inverse tangent of 3/4, you'll get 36.86. I'll write that off to the side.
Can't we just do times 0.8?
Yeah, you could do that as well. Now, this one turns out to be, and y'all might want to double check my work on this. This one turns out to be 3/1 sub x 172.57 times this is 103.54 newtons, and then F31Y is, again, this case it happens to be negative, so it's 172.57 with a negative sign in front of it times the sine of 36.86, which, like you said, is, in this case, it's going to be 0.6. So you get negative, in this case, 138.06. Okay. Now, all of this came from, as I told you,
Couldn't it be greater in the x direction than it is in the y direction in magnitude?
You would, oh no, okay, so that angle up there is like a 52-degree angle. So yeah, you'd expect the x to be larger than the y. And that,
Yeah, but if you're taking phi is at an angle from the y-axis, so shouldn't you have taken cosine of 36.86 instead of, or you should have taken sine of 36.86 instead of cosine?
Cosine definitely gives me, in the position that I have the angle, cosine is definitely giving me the x component. And being that that angle up there is 52, I would have expected the x component to be larger than the y component, and I got the opposite of that. So your argument sounds really good right now. That's bothersome. Let me write this real quick, just so we'll have it somewhere on here.
I think your values may be reversed. When I put in 172.57 times cosine of 36.86, I got 138.006 or 07.
Excellent. Thanks for catching that. So I copied the wrong ones. So this one should be 138.06 newtons. Excellent. Good job, guys. Awesome. Okay, so 138.06. And then this one, notice I'm leaving it here so we'll know what I did going with the video. But this one should have came out to be 103.54 newtons. So yeah, you're on the money. That's what happened. I copied the two magnitudes incorrectly. So is everybody in agreement with that? This is okay now?
Yes, looks right to me.
All right, so now we can say F3 sub X. Actually, I should probably go back to my blue color. Going back to my blue. F3 sub X is going to be 0 plus the X component of F31. So that's 138.06 newtons. And then F3Y is going to be me taking the negative 103.45. Excuse me, 0.54. And adding it to the 299.6. And that gives me 196.06. Dot right there. Newtons. Again, I carried a bunch of extra sig figs here. So now what we want to do is reconstruct that vector. And I'm going to do it this way. I'm going to say, here's my x-axis or my y-axis, and here's my x-axis. And I'm going to say that my force in the x direction is 138, which will be right about there. And then my force in the y direction will be about 196. So it should be quite a bit bigger. And this is 138.1, say. And then this angle right here will be theta. And this is the magnitude of F3. So I can use the Pythagorean theorem to get F3 by taking 138.06 and squaring it. And then adding to that 196.06 squared. And then taking the square root of all that. And I get 239.8. Newtons is the magnitude. And theta, of course, is equal to the inverse tangent of 196.1 over 138.1. So it's a inverse tangent and I get 54.85 degrees. Now that one I actually had two sig figs as well, so I really should be doing only that. So our F3 is in fact about 240 newtons at about 55 degrees. Okay. Any questions on that? Thanks for.
I'm getting like 221.
Did you? Let me see if I mistyped anything. I've got 138.06 squared plus 196.06 squared. Did you get 138 and 196?
Sorry, I'm using the wrong. I used the 103, not the 138.
Yeah, it's really easy to do that. You saw that I did it. I actually made sure I worked this before class, so I'd have all this written out up, and I wouldn't make such a careless mistake. Still didn't matter because I ended up copying down the wrong one and got my X and Y's reversed. So stuff happens, man. So does anybody have any questions on that? Now, your book offers a neat little follow-up problem to this. And I'm going to offer actually two of them. One, I can say, can you imagine somewhere you could put a positive charge, say Q, not Q1, Q2, or Q3, just a plain Q, such that the total force on charge 3 would then be 0? And if so, how big would that charge be and how close would it need to be? And is that a unique answer? Is that the only answer it could be? Could you do a positive charge somewhere else, or could you even do a negative charge? Anybody have any sense of what the answer to those questions are? Not necessarily give me the numbers, but
Doesn't it have to be? Aren't there infinitely many solutions along the line of 54 degrees?
yeah, exactly. So you'd want the if you took a positive force, since this one's pointing up and to the right at 54.9, you would take a positive force and put it up and to the right at 54.9 degrees from the Q3, and then you just use the Q and R that makes the magnitude equal to roughly 239.8. So yeah, that's exactly right. You could also use a negative one and put it at 54.9 degrees downward and to the left. So that would work as well. Only that would be an attractive force. So yeah, good job. I actually offer that as an extra credit. I'll put it in our module for week 1 if I want to do it. It just is good practice for you. Now, the other part of this that's a little more important here. Let me stop sharing the screen for a second. By the way, I do put that document that you just saw. That'll be on my Google Docs tonight. I usually export it as a PDF immediately, and it'll have the name PHY242N01B_082522. But now there was a problem with Coulomb's law, just like there was a problem with Newton's law of gravity. And Newton, said it. He's like, yeah, I don't know how the Earth could reach out and pull on the moon without some kind of tether, nor do I know how the sun could reach out and pull on the Earth without some kind of tether. But this explains exactly where the moon is and why it takes the time that it does to orbit around the Earth. So it's obviously a useful thing. I will keep working with it, and maybe one day we might know how that happens. But right now we just know that it does and just go with it. Well, Newton felt that way. Einstein, of course, felt that way, and that's why Einstein ultimately made his general theory of relativity, because it got rid of it. And electricity and magnetism, the same thing's going on, but it turns out we did something that we also tried with gravity that didn't quite work out so well. I mean, you could still work it out and get really as good a results as Newton did. But in the case of electricity and magnetism, we imagined in some sense that a given charge, let's say Q1, disturbs the space around it. In other words, it has an aura, as some of your more spiritual people might say. It's got an aura around it, or some of your people that believe in other things, like the I don't know, the Loch Ness Monster and stuff like that. They always say something crazy like an aura, but in this case, it actually works out. We imagine that the space around a charge is altered by the presence of that charge, and we call that alteration a field. So if you imagine taking, for instance, this room I'm in, maybe I point to that corner over there of the room down where the wall meets the floor, and I call that the origin of my coordinate system. And maybe along this wall behind my computer, And where it meets the floor, that's the x-axis. And along the wall to my right here, where that meets the floor, that's the y-axis. And along the corner vertically right there, there's a z-axis. Then this point right here has an x, y, z coordinate. If I give that x, y, z coordinate, say a temperature, in other words, I take the temperature exactly at the spot and I write it down. Now, instead of having a triple, a x, y, z, I have a quadruple. I have an x, a y, a z, and a t. That would be a scalar field. If I did that for all the x, y, z's, I added a t, that would be a scalar field called the temperature field. In the case of a vector field, I'm going to take each x, y, z and assign it a magnitude and direction. Or you could assign it e sub x, a e sub y, and an e sub z, in which case it's a six tuple. So you got x, y, z, e sub x, e sub y, e sub z. But that's a vector field, and that's exactly what we did. We imagined that the particle, any particle that has charge, disturbs the space around it by creating a field. And then when another charge gets in that field, it experiences a force. So how do we go about defining that? Well, that's actually a neat little thing. I'm going to show it to you now. Basically, what we do is we realize, hey, if a single charge has a field associated with it, then putting another single charge around here is going to actually alter that field, right? So we've got to think about the problems that arise as a result of that. So ultimately what we do is we call this electric field E, and the electric field is in fact E vector. I'm going to leave a space here on purpose. I'm going to take Coulomb's law for force, and I'm going to divide it by, say, Q2. So that takes out the Q2 part of F equals K, Q1, Q2 over R squared, because I want to be able to multiply the electric field by Q2 to get the actual force. But in order to do this such that the Q2 doesn't screw up the field, we have to imagine the scenario where Q2 is approaching zero. So in practice, you don't have to think much about it, but philosophically, you do have to remember there is a chance that because charge Q1 created a field and charge Q2 creates a field, if charge Q2 comes in the presence of charge Q1, then that's going to alter the field. But we want to minimize that effect. So philosophically, we imagine that Q2 is very small in comparison to the Q1. But it works either way. Ultimately, what that tells us is the magnitude of the electric field can be thought of as K. Since I divided out the Q2, I'll leave Q1 here over R squared, and that works fine. But more generally, we don't subscript it at all. We just say E is equal to K Q over R squared, okay? Or one more way, E is equal to Q over 4 pi epsilon naught R squared. So that's the electric field's magnitude. Now, what is the direction? The direction points in the direction a positive charge would move. So direction is the direction that a positive test charge would be compelled to move. So what does that mean? That means, for instance, if charge Q is right here and Q test is right here, then it has to act along this line connecting the two, right? And if Q was positive, then a positive test charge would be compelled to move off this way. Does that make sense? Okay. Okay, so that's the direction of it. Now, if you look back at this problem, notice the only difference here was we were using Coulomb's law, which is K Q1 Q2 over R squared. You can now, and this is the second extra credit problem. Actually, technically, it's a sort of almost like a third extra credit problem, but I'm giving you credit for two of them. You can now take Q2 and compute the electric field at 0.30 centimeters, right? In other words, along the y-axis, right where Q3 was. And then you can take Q1 and calculate the electric field at 0.30 centimeters. So that's the electric field due to Q1. Now you can add those two electric fields and you'll get the total electric field at 0.30 centimeters. Does that make sense to everyone?
Hold on, you were breaking up for a
Yes.
second there. Can you repeat what you just said?
Yeah. Okay. So looking back at the problem we just finished solving, that's what I've got on the screen right now. You can imagine where Q3 is up there at the point 0.30 centimeters. That's where Q3 is. Forget about Q3 for a second and compute the electric field at that location due to Q2. And then you can do the same thing at that location due to Q1. You'll have two electric fields at 0.30 centimeters, and you can add them like vectors, and you'll get the net vector electric field. So the extra credit problem I'm going to ask you to do is do that and give me the magnitude and direction of the electric field at 0.30 centimeters. This will all be typed up in the problem, by the way, so you don't have to worry too much about trying to write down my words. It'll be in there.
Wait, wouldn't it just be the ant 240 divided by 60 micro?
Absolutely, exactly, right? But now what you're going to do is then you're going to multiply that electric field times the 60 microcoulombs, and you'll see that it is in fact exactly the same force. So yeah, but you're exactly right. That's another way you could do it, but it's a worthwhile practice just to see if you can get the exact same answers. So that's the extra credit I'm asking you for. Again, the way extra credits work is I create it, I put zeros in there. If someone does it, then and they do it, 85% correct, I change it to 100. But I also increase the number of dropped homework by 1 for each extra credit I give. Does that make sense? So don't worry, you're not required to do it, but it's a worthwhile thing. And yeah, you're absolutely right. It's just that force, or excuse me, yeah, that force F3 divided by 60 times 10 to the negative 6. All right. So now that y'all sort of got a feel for that, and I don't think I need to spend too terribly much time differentiating between that. What I'm going to do now is I'm going to derive a vector expression for this electric field that will allow us to easily calculate. I say easily, you're not going to believe that when I say it when we do it, but to easily calculate the electric field due to a distribution of charge. So to do that, I'm going to kill this line right here. I'm going to take my blue marker and I'm going to imagine a coordinate system, a three-dimensional coordinate system that looks like that. And I'm going to imagine a little chunk of charge. Okay, I guess it's going to be a sphere then, and a little point in space. Well, I guess it's going to change that into that. So let's do that. Okay, so here's a point in space. I'll call P like that. And that's me trying to make it look fancy, like cursive. And this is a little charge dq. Okay. Now, in principle, there is a vector that points to P from the origin, and I'll call that R sub P. There's also a vector that points from the origin to dq, and I'll call that R sub dq. Okay. Now, can anybody tell me a vector relating R2 or RP and RDQ or just RP or just RDQ such that that new vector will actually point along the line connecting these 2 points. So let's imagine, because we know, according to Coulomb's law, the electric field has to be along this line. Can you guys think of a vector or a vector operation that can be done on these to make a vector parallel to that little green dotted line I just made?
Is it some kind of vector addition?
Could be. What do you think? Imagine if, for instance,
Wouldn't it just be RP minus RDQ is equal to RDQP?
perfect. Yes. So in fact, yes, the vector that we're wanting is going to be this guy. And that is RP minus RDQ. Okay. Notice if DQ is positive, then RP minus RDQ points in exactly the right direction. That's the key point, right? Because electric field's supposed to point in the direction that a positive charge will be compelled to move if you put it there. So if I put a positive charge at P and DQ was positive, then the direction would be parallel to RP minus RDQ. Therefore, we can say that the differential electric field is in fact dq over 4 pi epsilon naught. Actually, let's not do that last thing there. Let's do an absolute value bar RP minus R dq. Notice the length of that vector is exactly the R that we use in Coulomb's law. But now to make it a vector, I'm going to multiply by RP minus R dq. Does anybody see a problem with that?
RP minus RDQ might not have a value of 1. You need to make it a unit vector.
Exactly. If you made it a unit vector, it would work. And the way you make a vector a unit vector is you divide it by its magnitude. So what I'm going to do instead is change this to 3. Does that make sense? So this is an equation your book doesn't give you. Yeah, he almost gives it to you. He gives it to you in Coulomb's law for the force, but he doesn't give it to you for the electric field. That being said, it can still be on your equation sheet. So my rule is your equation sheet can only be the equations that the author has numbered, like 21-9. But this is one that you're allowed to have on your equation sheet as well. And we're going to use it now. So you guys ready to see some cool calculus? Anybody have any questions before we move on? Does it all make sense to some extent? I know you don't know yet how you're going to use it, but I'm going to show you that. Now, one thing to keep in mind is when charge is distributed in one dimension, it's often convenient to say dq is equal to some charge per unit length times dl, or if it's distributed uniformly or not uniformly over some surface, two-dimensional surface, then it's useful to call it some charge per unit area times dA. Or if the charge is distributed out through a volume, it's useful to call to use the charge per unit volume rho and multiply it by dV. So that's the 3 forms that dq will take when you're doing these problems. Okay, so notice the lambda would have units like coulombs per meter, sigma would have units of like coulombs per square meter, and rho would have units of like coulombs per cubic meter. Does that make sense to everyone?
Yes.
Okay, so our first problem is going to be this. That actually turned out pretty good. Okay, cool. So this is my x-axis, this is my y-axis, and this is my z-axis. And I'm going to say this is a distance Z up here, and this is the point P that I had talked about. This is actually a line of uniform charge. So basically that tells us it also has, one second, let me finish that sentence first. A line of uniform charge lambda with total charge Q. So that means since this radius right here is R, that means lambda is equal to Q over 2 pi R. Does that make sense? That's my way of saying, okay, that's what I mean, guys. This is what I mean by lambda. It's the total charge divided by the length in this case. And since it's uniformly distributed, it's actually a constant. So that's why I was able to just take the Q and divide it by 2 pi R. If it wouldn't have been uniformly distributed, I'd have to have lambda as some kind of function of theta or something like that. So this is just a ring of charge. Let me write that instead of line of charge. Like a ring of fire. Burn, 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 a ring of fire. No. Okay. So what I want to know is what is E at P? Okay. So first off, I've got to remember my formula says DE is equal to DQ over 4 pi epsilon naught. Oh, actually, RP minus RDQ cubed times RP minus RDQ. Now, this seems like a bloody mess, right? This is a nightmare. That's terrible. But no, it's not. It's actually a very stepwise possible way of treating this. So all we have to do is identify the parts and then calculate what they are. So first off, I'm going to draw RP. Can anybody guess what RP looks like?
Straight up.
Yep, it's going to be this. So there's my RP. And I'm also going to draw, well, actually, I didn't go far enough. I'm also going to draw my R DQ because I'm going to say this little guy is DQ, which is lambda times the distance around. If I allow theta to change by d theta, then it'll be R d theta. So this vector right here is R dq. Does that make sense to everyone?
Yes.
Okay. Now, here's the problem. I'm using cylindrical coordinates, basically. That's why I included those in that week 0 stuff. You don't have to know too much about it, but just know that, you know, hey, that angle going counterclockwise from the positive x-axis towards the y-axis is just theta. The distance away from the origin is another variable called r. And just like we have an I hat, j hat, and k hat, there exists a r hat, a theta hat, and a k hat for cylindrical coordinates. But if we ever use those hat vectors, we've got to integrate them and differentiate them. But if we use the ijk vectors, they can just be pulled through a vector or through an integral or a derivative with no change whatsoever. So we use them as symbols to help our understanding the r hat, the theta hat, or the r hat, the theta hat, and the phi hat in the case of spherical coordinates. But in general, when it comes down to computing, we don't do them because they're ugly and they're nasty. But what we can see here is the beginnings of it. So what I'm going to do now is I've got to write my vector RP. So I bet y'all can guess what RP looks like. How long is it and what direction is it in?
It's in the k hat direction at
Exactly.
P length.
Yep. And how about this one's a little more complicated. I need to get an x component. So I'm going to say R dq is actually equal to R cosine theta I hat plus R sine theta j hat. Now, the reason why I kind of quickly come up with that is one, I've been doing this for a long time. I'm an old man, but also it happens to be that r hat is really just cosine theta I hat plus sine theta j hat. And then if you take the derivative of that dr hat over d theta, that gives me theta hat too. We're not using those, but that's just a neat little sidebar. And when you see those kind of things, certain equations in your dynamics class will look a lot more reasonable. Okay, so I'll just leave them there for right now. Now we've gotten RP and we've gotten RDQ, but our formula says we have to compute RP minus RDQ. And then we got to compute its magnitude. But RP minus DQ, notice is just Z K hat minus R cosine theta I hat minus R sine theta J hat. And then, of course, the magnitude of RP minus RDQ. I think you can realize that this vector RP minus RDQ is technically this vector, right? That's RP minus RDQ, is that green vector I just drew there. And I think you realize that those two sides are perpendicular. So really, the magnitude is just the square root of Z squared plus R squared. You can also get that by the trig identity, sine squared plus cosine squared equals 1. But either way, that's what the magnitude is. So now I can say E is equal to, actually, I don't want to say that. I want to go back to my blue. I can say E is equal to the integral of DE, which equals, I'm going to have a lambda up there, which is constant. So I'm going to pull that out in front. The 4 pi epsilon naught, I'm going to pull out in front. And I'm going to say integral of, now what I've got left in my DQ is just RD theta. So I could have pulled that R out, but it's going to be RD theta. And I know this will make the math teacher's screen, but we can actually write this after the integral and still realize that we have to integrate it. Ooh, that's supposed to be that. And all that will be over the square root Z squared plus R squared, which notice neither of those are being integrated. So I end up getting lambda R over 4 pi epsilon naught square root Z squared plus R squared times the integral of Z d theta K hat theta equals 0 to 2 pi minus R cosine theta d theta I hat minus R sine theta d theta j hat. Now there's a lot of things that can go on here. One thing I think you'll notice is if DQ is right where I have it drawn, then diametrically opposed back here is another DQ that, notice, it will have a Z component in the exact same direction as the force or the electric field due to that first DQ, but the X and Y components will exactly be opposite. So from the symmetry of this problem, physics would tell us that this should have no I hat component and it should have no J hat component. And that's true, and we can work it that way. But I'm going to actually show you as well that it is. Okay, so we expect these last two integrals to go to 0. I think you can immediately see what this first integral is going to be. The integral of Z d theta from 0 to 2 pi is just 2 pi Z. So what I get is E is equal to, let's write it this way. I'm going to say lambda times 2 pi
Should the quantity of square root Z squared plus R squared be
thank you, cubed. Yeah, thank you. And I didn't even write that over here. Good job. Yeah, that's right. So 2 pi R and then I'll put the z over here, and then it'll be 4 pi epsilon naught z squared plus r squared to the 3/2. And that's all in the k hat direction. That's actually the total answer. And in a physics class, basically you just make that statement about the symmetry and you turn that in, and lo and behold, you got 100. Okay. But you could also realize, remember, lambda was q over 2 pi r. So we can also realize that that E could also be equal to q z over 4 pi epsilon naught z squared plus r squared to the 3/2 in the k hat direction. And that's perfectly acceptable as well. Okay. Now, what actually happened in the other case? Well, the other case, the integral negative r cosine theta d theta from 0 to 2 pi. Well, we know that cosine theta looks like that. And we also know that this area is equal to this area plus this area. So the integral equals 0. Similarly, negative r integral 0 to 2 pi sine theta d theta. We know that the sine graph looks like this. And this area right here is exactly equal to this area. So the integral is 0. So that's another way of doing it. Of course, you could also just evaluate the integral of cosine. Since the derivative of sine is cosine, the integral of cosine is sine. So we could just say sine of 2 pi minus sine of 0, or excuse me, sine of 0 is equal to 0. And this one, of course, the integral of negative sine is cosine. So we could say the cosine of 2 pi minus the cosine of 0 is also equal to 0. So there's 3 ways that we could get rid of that. Any questions on that one? All right, so let me show you a more robust one. Okay. So I'm going to start my problem in red again. I'm going to draw my y-axis like this, and I'm going to draw my x-axis like this. And now I'm going to imagine a wire along the y-axis that's actually uniformly charged, and it's infinitely long. Okay. Oh, that's really looking bad. So we're saying I've got a point P here that's a distance r away, and I would like to know what is the electric field at that point. So to do this problem, I'm going to say dq is equal to lambda dy. And I'm going to draw dq right here. Okay. And I notice that this distance right here is in fact y. And actually, let's erase that. This point right here is y. And then this is, of course, r dq. And then this vector right here is rp. Okay. So y'all can try to guess what r dq is and what rp is. I'm going to go ahead and write them out. Everybody agree with what I found there so far? So E is going to be equal to the integral of dE, which is going to be obviously a lambda over 4 pi epsilon naught times the integral of dy over, now I'm going to say r squared plus y squared. This time I'll remember my exponents of 3, and I'll say r I hat minus y j hat, like that. And I'm going to integrate from y approaching negative infinity to infinity. So let's take E sub, for starters, let's see, from symmetry, is there any component of the electric field that you think is not going to exist? By symmetry? Let me show you something on here. I'll use this red. That is RP minus RDQ, at least direction wise, right? And you see that if I have another differential mass element down here, then that's going to point upward and to the right. So you expect the actual y components to be 0. Okay. By symmetry, of course, also you expect the z component is going to be 0 because that's not playing a role in here at all. And of course, you would be right. But that's not very relevant to this problem. Okay. So I'm going to start off by working E sub x. And that's going to be lambda over 4 pi epsilon naught times I hat. Well, actually, no, I'll leave off the I hat since I called it a E. Well, actually, I could do this. Whoa, Nelly, I couldn't do that. I'll put the I hat there. And now I'll say the integral of R over r squared plus y squared to the 3/2. Okay. Now let's let y equal r tangent theta. Then dy, this is called a trig substitution, dy is equal to r secant squared theta d theta. And y approaching negative infinity implies theta going to negative pi over 2, and y approaching positive infinity is the same thing as theta approaching pi over 2. So that's something we can keep in mind. So now I'm going to have lambda times r times I hat over 4 pi epsilon naught times the integral. Oh, I also left off my dy up here. Put it back now. Okay, so lambda times r times I hat over 4 pi epsilon naught. Now I've got dy is actually r secant squared theta d theta. And down here in the bottom, I have r squared times 1 plus tangent squared theta, all that to the 3/2. And this could definitely look a little better. Okay, now you see that basically I've got an r squared in the numerator, and in the denominator I got an r squared raised to the 3/2 power. So that's going to make that into an r cubed. So ultimately I just get lambda over 4 pi epsilon naught r in the I hat direction times the integral of secant squared theta d theta under, now 1 plus tangent squared is equal to secant squared theta. So I've got a secant squared theta raised to the 3/2 power. So that's secant cubed theta. So ultimately this just becomes lambda I hat over 4 pi epsilon naught r times the integral cosine theta d theta from negative pi over 2 to pi over 2. Now cosine is what we call an even function, meaning cosine of negative theta is the same thing as cosine of theta. So we could actually change this, multiply it by 2, and then change it to the integral from 0 to pi over 2. But really all that's going to happen is then you get a cosine of the integral turns out to be the sine of 0, or excuse me, the sine of 2 pi or pi over 2 minus the sine of 0, which is just 1. So you get 1 and then you've canceled out 2. But either way, the ultimate result is lambda over 2 pi epsilon naught r in the I hat direction. And that is the total electric field. Because by symmetry, we can't argue E sub y is equal to 0. Now I'm going to actually show you that E sub y is 0. We're out of time, but I'm going to show you really quickly. If I want to do the E sub y, notice all I have is a negative y dy over r squared plus y squared to the 3/2 power. Well, this one you can just do a regular substitution. We could say let u equal r squared plus y squared, then du is equal to 2y dy. Well, we've got a y up there already, so I can say this is going to be negative 1/2 integral of du over u to the 3/2, because putting a 2 down the bottom is the same thing, is canceled out by putting a 2 up top, and then a 2y dy is just du. Now we can say, okay, well, that's easy enough. That's -1/2. The integral of du times u to the -1/2 is, or excuse me, -3/2 is basically -2 times u to the -1/2. Well, if you now do negative times a negative, that gives you 1. I get r squared plus y squared square root in the denominator. I'm going to evaluate that from y approaching -infinity to y approaching +infinity. And you can see that's essentially going to be 0 minus 0. Because you have to take the limit as y approaches infinity. And of course, as y approaches infinity, the r can just be thrown away. So you're taking the limit of 1 over y as y approaches infinity, and that gives you 0. And then you're taking the minus the limit of 1 over y as y approaches -infinity. And that, of course, gives you 0 as well. Any questions on that?
Plenty.
All
But
right,
I don't think we have time.
Yeah, his time's up. We've done more than enough. You guys are free to go. Also, there's one more integral problem, but you can find that on my YouTube channel in one of the videos for chapter 21. Look that up if you'd like. But basically, we can take that result that we got for the ring of charge, and we can now integrate it and in a different way than we just did here, and get an integral or get an electric field for a large flat disk. That's pretty much all that I haven't integrated. Other than that, we would do the electric dipole stuff, and the electric dipole stuff is just recognizing that an electric dipole is two oppositely charged, one positive, one negative. And if you take the charge that it has times the distance between them, and then make it a vector pointing from the negative charge to the positive charge, that vector is called P. And it turns out the torque on a dipole and electric field is P cross E, and the potential energy of the dipole and electric field is negative negative P dot E. So those are some results. I don't feel too compelled to cover the dipole stuff, but I really feel bad about not doing the other electric field. So I'll probably at least find exactly what video that is and send you a link to that. But you guys are free to go. Thanks for coming. I'll wait for the last person to leave in case anybody has any questions. And you're always welcome to attend one of my lectures face-to-face, or one of my lab sessions, which I use as office hours too. If this is a little much, I realize this is a tough course to take over the internet. So I just offer that in case anybody needs anything. Thanks
Thank
for
you.
coming, everyone.
Thanks.
Thank you. Have a good weekend.
You too. Robert, do you have a question? All right, you might be gone already. Have a good day, everyone.